Hey everyone, I thought I'd show you my latest project. This is a plastic chamber that I built that's holding liquid CO2. So first I'll show you how this thing works, and then I'll talk about how I built it and what I plan to do with it. So the chamber is built from a piece of aluminum with acrylic on the front and the back, and it's designed to be heated slowly, and I'm using this strip heater. This is just a flexible fiberglass covered heater that's normally used for bending acrylic, or at least that's what I normally use it for. I guess they're also used for heating pipes. You can wrap it around a pipe. In this case, I'm going to wrap it around the chamber. Like that. And I think this heater is about a couple hundred watts or something on that order. So we have liquid CO2 inside there, the heater on, and I'm going to plug the heater in. Right now the pressure gauge is reading about 700 psi. I drilled a tiny hole in there just so I can put a thermocouple in and get a more accurate reading. You can see the CO2 is starting to boil in there. Okay, now the boiling has pretty much stopped. You can still see some density changes in the liquid there, but at this point there's no more bubbles, and the transition from the liquid to the gas phase in there is almost gone. So let me give it another shake. And as you can see, something interesting has happened. There's no more dividing line between liquid and gas inside there. So I'm going to unplug the heater. And give it a few minutes for the cloudiness to subside. So as you can see, what we're left with here is one phase basically inside the chamber. The CO2 has gone supercritical, meaning that the density between the liquid phase and the gas phase eventually became so similar that they blended together. So it's all one continuous phase in there now. Now to transition back, what I'm going to use is just a piece of dry ice, and I'm going to hold it against the aluminum on the outside here to bring the temperature down quickly. So check this out. Surprisingly, this actually works better with just water ice, since it melts and makes a nice contact between the aluminum and the ice cube. But as you can see, we're back to two phases. So I built this chamber by getting an aluminum disc with a hole already in it, and I turned it down and faced it, and then turned the inside, and then mounted it on the mill and drilled the holes first for the bolt circle. And then, since there's a groove that holds an O-ring in there, and the bolts are so close to the O-ring, or rather the part is so small it would have been difficult to clamp to cut that O-ring groove. So what I did is I tapped the holes in the mounting surface on the mill, and then temporarily used some screws just to hold the piece down, and then cut the O-ring groove. So same on the other side, just exactly the same. And then I also used the mill to cut out these plastic parts with the same bolt circle, and put an O-ring in there and sandwiched it all together. One interesting problem that I ran into is that there's no valve on this chamber. So what I do to fill it is just put half of it together, drop a few pieces of dry ice in there, and then then screw the other side down. But this ends up being a problem because the pressure builds before I have time to actually get the chamber sealed up to the proper torque. So the O-ring is severely deformed because it was under a lot of pressure even as I was closing the chamber. You can see the O-ring is kind of squeezed out into the space between the plastic and the aluminum. The gland was actually carefully designed so that the O-ring would crush down in there and fill up the space in the gland, but it actually still managed to seep out. Same on the back side. I used actual engineering formulas to determine the thickness of acrylic that I would need for this, and I was anticipating much higher pressures. So the CO2 starts to go supercritical at around 1,000 or 1,100 psi, but I designed this chamber thinking that I would actually encounter much higher pressures, 2, 3, or even 4,000 psi. If I raised the temperature high enough, obviously the pressure of the supercritical fluid would go higher. So initially, when I first set this up, I was a little worried about the thing rupturing because who knows what's going to happen. So what I did was I set this up in a corner of my shop with a camera on it and plugged in the heater to a long extension cord so I could watch this thing on a TV monitor far away and then turn the heater on and off and monitor the temperature and pressure. So I got it up to 120 or 30 degrees Fahrenheit, and the pressure was still under 2,000. So I'm not sure. Maybe I'll try putting more dry ice in so that there's more volume inside there to see if the pressure is going to be higher. I don't know. But anyway, so what are you going to do with supercritical CO2? The first thing I want to try is putting green coffee beans in there and see if I can extract the caffeine from them. One of the commercial uses of this process is to decaffeinate coffee beans. But of course the caffeine doesn't get destroyed, it just gets pulled out. So you can refine it. Another interesting use for supercritical CO2 is dry cleaning. So you can put something in there that has a solvent or that has an oily substance on it and remove the oily substance without using water or a hydrocarbon solvent. Okay, well, I hope you enjoyed that. Let me know if you have any suggestions for what I should do with supercritical CO2. All right, see you next time. Bye.